Welcome to the deep dive. We're here to cut through the noise and get straight to, well, the really interesting stuff from cutting-edge research.
That's the plan.
And today, we're diving into something that's genuinely reshaping AI. You know how large language models, these LLMs, are just learning incredibly fast?
Oh, absolutely. It's pretty astonishing. Like hyper-speed students.
Exactly. But there's a catch, right?
There always is. And here, the core challenge is that these powerful models, well, they need huge amounts of really good data to learn from.
High-quality data.
High quality, yes. And getting that from humans, it's becoming a real bottleneck.
Why is that?
Well, think about it. It's expensive. It takes a lot of time. There aren't always enough people with the right expertise. Major privacy issues, too.
Right.
Plus, let's be honest, even the best human data can have, subtle biases or just plain mistakes. It's not always perfect for fine-tuning these incredibly sensitive models.
Okay, so if human data has these drawbacks, what's the alternative? Where do we go?
This is where synthetic data comes in. It's basically artificially created data, designed to look and act like real-world stuff.
And it's actually working.
It's emerging as a really viable, very promising alternative. Yeah.
So that's our mission today, unpacking this synthetic data solution.
Exactly. We're going deep on a specific cutting-edge method called CoT-Self-Instruct. That's chain of thought self-instruct.
Chain of thought self-instruct, okay.
Think of it like this. We're teaching the LLM student how to think critically about the subject before it starts studying. And then, maybe even more importantly, how to grade its own practice questions to make sure it's actually getting it right.
Wow, okay. So it's not just about feeding it data, but making the data generation itself smarter.
Precisely. We'll look at how it really changes the game for creating high-quality synthetic data and how that ultimately makes LLMs perform better. Much better, actually.
So for you listening, think of this as your shortcut. We're boiling down the complex stuff, focusing on what really matters in this field that's just moving so incredibly fast.
Hopefully giving you those aha moments.
Exactly. Those insights you can actually use. Right, let's get into it.
Let's do it.
So, CoT-Self-Instruct. You said it builds on an older idea, self-instruct. Maybe give us the quick version of that first.
Sure. Yeah, the original self-instruct was, well, pretty clever for its time. The basic idea was that an LLM could actually generate its own examples.
Its own training data.
Kind of, yeah. Instruction following examples, you'd give it a few really good examples like prompts or questions. These are the seed samples.
Okay.
And then the LLM would try to generate more examples that were similar in style and complexity.
Trying to copy the good ones.
Basically, yes.
Yeah.
And people tried different ways to make those generated examples more diverse or complex. But the big challenge, the real sticking point, was quality. You could get a lot of examples, but were they actually good for training? Were they effective? That was the hard part. It was like our student churning out practice problems, but, maybe half of them were flawed or didn't really test the right thing.
Gotcha. So quantity wasn't the issue, it was the quality control.
Exactly.
Okay, so this is where CoT-Self-Instruct comes in and, well, gets interesting. How does it actually tackle that quality problem?
Right. The big innovation here is that CoT-Self-Instruct makes the LLM reason and plan first. It uses this process called chain of thought, CoT, before it even tries to generate a new synthetic instruction.
Chain of thought. That's the step-by-step reasoning process we've talked about before.
That's the one. So instead of just saying, give me more like this, it's a much more structured approach. The LLM is prompted to actually think through how to create a good instruction, almost like outlining an essay before you start writing the paragraphs.
Okay, that sounds much more deliberate. Can you walk us through that creation stage? What's happening under the hood?
Yeah, so picture this. CoT-Self-Instruct doesn't just ask for a new instruction directly. First, it tells the LLM, okay, look carefully at these seed instructions you were given.
Analyze the examples.
Exactly. Analyze them. Think about their domain. Is it math, coding, creative writing? How complex are they? What's their real purpose? It's about understanding the essence of a good, useful prompt in that specific area.
So the LLM is sort of reflecting on the input first, asking itself, what makes this prompt good?
Precisely. It's metacognition for the AI, in a way. Then, after that analysis, it uses chain of thought, that step-by-step reasoning, to come up with a plan for a completely new, self-contained instruction.
A plan first.
A plan first. And the goal is to make this new instruction match the quality and complexity of those original seeds. This whole multi-step thinking process, the CoT part, that's really the key to generating better data from the get-go.
It's like the student saying, okay, I see the kind of thinking needed here. Now let me design a new problem that genuinely tests that specific skill.
That's a great analogy, yeah.
And you mentioned it handles different types of tasks. Two main kinds.
Yes, that's important. First, you have verifiable reasoning tasks. These are things with a single deterministic correct answer. Think math problems, logic puzzles, stuff like that.
Where there's definitely a right answer.
Exactly. For these, the LLM using CoT-Self-Instruct generates both the new instruction and the verifiable target answer.
Oh, interesting. So it creates the problem and solves it.
Right away, yes. For example, it might generate a complex algebra problem like find the value of k such that this system of equations has infinitely many solutions, and then immediately provide the correct answer, say k.
Wow. So it's ensuring the problem is actually solvable and valid from the start. It's like writing the test and the answer key at the same time.
You got it. That's a huge quality check right there. Then the second type is general instruction following tasks. These are more open-ended.
Like creative writing or asking it to generate code?
Exactly. Writing prompts, coding challenges, summarization requests, things where there isn't one single right answer. For these, the LLM just generates the instruction itself.
So how do you know if those instructions are any good?
That comes later, during curation. The responses generated for these prompts get evaluated by something called a reward model.
A reward model.
Yeah. Think of it as another, usually smaller, AI that's been specifically trained to judge the quality of an LLM's output. Is it helpful? Is it coherent? Is it safe? It gives the response a score.
Okay.
And one important strategy they use here, especially for these general tasks, is categorizing the initial seed prompts. Separating writing and storytelling from technical and programming.
Why do that?
It helps prevent the LLM from creating weird, unnatural prompts by trying to mash unrelated concepts together. Keeps the generated data focused and useful within a domain.
Makes sense. Keep things coherent. Okay, so the creation process is much smarter, much more reasoned, but you said even smart LLMs aren't perfect. What about this curation stage? Filtering out the bad apples?
Absolutely critical, yes. Even with this advanced CoT creation process, not every single generated instruction will be gold. So you need a really robust filtering step curation to only keep the high-quality stuff for the actual training data set.
Like our student proofreading their homework.
Exactly like that, double-checking the work.
And the filtering methods are different for the two task types,
Okay.
right?
For those verifiable reasoning tasks, the ones with the single right answer, they use a really neat method called answer consistency.
Answer consistency, how does that work?
Okay, so remember, for these tasks, CoT-Self-Instruct already generated both the instruction and what it thought was the correct answer using that deep chain of thought process.
Right, the initial answer key.
Yes. Now, for filtering, they take that instruction and have the LLM generate multiple answers to it again, maybe, say, 5 or 10 times, just standard generation without the deep CoT reasoning this time.
Okay.
Then they look at those 5 or 10 new answers and see what the majority answer is. Like, if 7 out of 10 times the answer is 42.
A consensus answer.
A consensus answer. Now, here's the key. If that majority consensus answer doesn't match the original target answer, the one generated way back during the CoT creation stage, the whole example gets thrown out, instruction and all.
Wow. So it's checking its quick consensus answer against its initial deeply reasoned answer.
Exactly. It's basically saying, my first, most careful thought process gave me answer X. If I can't consistently get answer X when I try solving it multiple times quickly now, then maybe the original problem or my initial solution was flawed. It's a really strong quality check.
That is clever. It trusts its deeper reasoning more.
And the research shows this works better than the standard self-consistency filtering, precisely because that initial CoT-generated answer provides such a strong, reliable benchmark.
Okay, makes sense. So what about the other kind, the non-verifiable tasks, the open-ended ones? How do you filter those without a single right answer?
Right, different problem, different solution. For those, they use something called RIP filtering, that's rejecting instruction preferences.
RIP filtering. Sounds dramatic.
Huh? Yeah. It's quite effective, though. Here, you take a generated instruction, and again, you have the LLM generate multiple responses to it. Not answers, but full responses, like writing a short story or a code snippet.
Okay.
Then, each of those responses gets evaluated by that reward model we mentioned earlier.
The quality judge AI.
Yep. The reward model gives each response a score. Now, the filtering decision is based on those scores. A common way to do it is to look at the lowest score among all the responses generated for that one instruction.
The lowest score. Why that one?
The thinking is, If an instruction can lead the LLM to produce even one really poor response, according to the reward model, then maybe the instruction itself isn't consistently good enough. It might be ambiguous or flawed.
I see. So it's like a prompt is only as good as the worst response it can elicit.
Kind of, yeah. It's a conservative approach. You only keep the prompts that tend to reliably produce good responses across multiple attempts. Prompts that consistently get high scores from the reward model are kept.
That's really interesting. So the LLM is not just the student creating the homework, but also the grader using these sophisticated checks.
It's acting as its own quality control mechanism, exactly. Thinking it through, creating it, and then rigorously checking its own work before it's used for actual learning. That student grading their own homework idea really fits.
Okay, this all sounds incredibly well thought out, but you know the million-dollar question. Does it actually work? What's the impact on LLM performance? Does it make them smarter?
The proof is in the pudding, right? And yes, the data is pretty clear. Models trained using data generated by CoT-Self-Instruct, especially with the filtering, consistently gave the best results.
Better than other methods.
Better than standard self-instruct, and importantly, often better than models trained on human-created data. It's a really significant finding.
Okay, let's break that down. Reasoning tasks first. How did it stack up against the standard self-instruct?
So just baseline, no filtering yet. CoT-Self-Instruct achieved an average accuracy around 53% on the reasoning benchmarks they used. Standard self-instruct was lower, around 49.5%. So a noticeable improvement just from the smarter generation.
Okay, a decent bump.
But then you add the filtering. That's where things get really interesting. With that answer consistency filtering we talked about, CoT-Self-Instruct jumped up to 57.2% accuracy.
Nice.
And that was significantly better than standard self-instruct, even when it used its best filtering method, which only got it to about 53.6%.
Yeah.
So CoT plus smart filtering clearly leads.
Okay, leading the synthetic pack. But you said compared to human data, this is the part that sounds almost, well, unbelievable.
It surprised a lot of people, I think. But yeah, the results are quite compelling. They took a set of existing, high-quality, human-annotated reasoning questions, about 900 of them. Training on that gave an accuracy of about 44.6%.
Okay, the human baseline.
All right. Now, they trained another model using filtered CoT-Self-Instruct data. They used about 3,000 prompts, so more data. But remember, it's synthetic. That model achieved 57.2% accuracy.
Wow, that's a huge difference. 44.6% for human data, 57.2% for the synthetic CoT data.
Exactly. And even when they matched the amount of data training on only 900 filtered CoT-Self-Instruct prompts to match the human set size, the CoT data still won significantly, getting 54.2% versus the 44.6% for human data.
So it's not just about having more data, it's that the synthetic data is somehow better, higher quality.
That's what it strongly suggests. The quality really seems to trump quantity here. And they even scaled it up. Further training on 10,000 filtered CoT prompts pushed accuracy even higher to 58.7%. It demonstrates that this method can generate high-quality reasoning data that's actually more effective for training than some existing human data sets.
That really flips the script on just get more human data. Quality over quantity seems to be the key message here.
It certainly looks that way for these kinds of tasks.
Okay, mine's slightly blown on the reasoning front. What about the other side, the non-verifiable tasks? Creative writing, coding, general instructions. Does CoT hold up there too?
Yes, it does. Same story, really. Comparing CoT-Self-Instruct to standard self-instruct, again without filtering first, CoT scored higher based on the reward model evaluations, 53.9 versus 47.4 for standard.
Another clear win for CoT generation.
Right. And interestingly, they explored whether more reasoning helps during the CoT creation stage.
Like making the chain of thought longer.
Exactly. Asking the model to provide a more detailed, longer reasoning chain before generating the instruction. And yes, they found that doing so provided even bigger gains. It reinforces that the depth of that initial thinking step really matters. The more that the student thinks, the better the question they write.
Fascinating. And the RIP filtering, did that help here too?
Oh, yeah. Applying RIP filtering boosted the CoT-Self-Instruct performance further, up to 54.7.
Okay.
But here's another interesting bit. They also tried applying RIP filtering to a data set of human-generated prompts from a set called WildChat.
Filtering human data.
Yeah. And it actually improved the performance of models trained on that human data, too, from about 46.8 up to 50.7.
What does that tell you?
It suggests that, well, human-generated data can be pretty noisy itself, right? Not every prompt humans write is perfect. So these filtering techniques have value even beyond just synthetic data. They can help clean up human data too.
That makes sense. Even human stuff needs quality control. So putting it all together for these general tasks.
Putting it all together, the best models were the ones trained with CoT-Self-Instruct plus that RIP filtering. They hit that 54.7 score.
And how did that compare to the human data?
It clearly beat models trained on just the raw human prompts, which scored 46.8, and even beat the filtered human prompts, which scored 50.7.
So synthetic still wins, even against filtered human data?
In these experiments, yes. And even when they use more advanced training techniques later on, like DPO, which fine-tunes based on preferences, the model initially trained with CoT-Self-Instruct plus RIP filtering still came out ahead, 67.1 versus 63.1 for the model starting from human prompts.
It's just consistently better. Across the board, CoT-Self-Instruct seems to be delivering superior results.
The evidence points strongly in that direction.
Yeah. Okay, what a journey through this. Let's try and recap the core takeaway here. We've seen CoT-Self-Instruct as this really powerful new way to create and curate synthetic data for LLMs.
Right. It's a pipeline. First, you instruct the LLM to reason about the data it needs to create using chain of thought. Plan it out.
Make it think first.
Then, after it generates the data, you apply these really smart filtering techniques. Answer consistency for the verifiable stuff, RIP filtering for the more open-ended tasks.
To keep only the best example.
Exactly. And the result is incredibly high-quality training data.
And this high-quality synthetic data significantly boosts LLM performance in both complex reasoning and general instruction following.
Consistently outperforming not just older synthetic methods, but also, crucially, existing human annotated data sets in these studies. It really hammers home that idea. Data quality might be much more important than just raw data quantity.
It feels like a fundamental shift. It's like, as you said, the student isn't just learning from textbooks anymore. They're learning how to write better textbooks for themselves.
That's a good way to put it. They're becoming active participants in their own learning process, generating the very material they need to improve.
So that leaves us with a pretty provocative thought, doesn't it? If LLMs can now effectively teach themselves by generating their own superior training data, I mean, what does that unlock?
It opens up huge possibilities, right? For the future of AI development itself, maybe faster, more efficient progress, but also maybe for our own learning too.
How might this change how we interact with information, how we learn, what we even prioritize learning if AI is becoming so adept at creating and mastering knowledge itself?
It's definitely something to think about. What does it mean when the student can not only ace the test, but also write a better test than the teacher? Where do we go from there?
A fascinating question to ponder. Thank you for that deep dive.
My pleasure. It's exciting stuff.